let me give a recap of the virial theorem, which I did last time. Now, in the notes, I have given the detailed derivation. There was an error which was there in the lecture, both in the original one as well as in the repeat one. I have corrected that in the notes which I have given, and I think also in the and the notes I have given, which I have circulated. Now, we will not be requiring the detailed derivation of the virial theorem. So we will only look at the result and see how it can be used for astrophysical applications. So the virial theorem basically says that d2 by dt square of half summation mi xi dot xi, where this is summed over all particles, equal to 0. That is when the system is virialized. Okay. Fine. So now, and what happens is when you have an interaction potential, which is a power law, which means that the potential between any two particles is a power law of the form the distance to the power n. Then for a virialized system, I have twice the total kinetic energy is equal to n times the total potential energy. And this is a consequence of this, which I have shown in the notes. Now, for us, what is relevant is the special case where n is -1. Because for gravity, the potential goes as 1 by r. So n is -1. And from this, we get that for gravity, for a virialized system, we have twice the kinetic energy plus the potential energy is equal to 0. And I have given some problems also using these virial theorems. And I think what we need to do is, see, next Saturday, I will not be taking the class, but the Saturday next to that, we will discuss the problems corresponding to all these 3 lectures before we proceed. Is that fine, or can you hear me?
Yes, sir.
Yeah. Okay. So one of the applications of the virial theorem is heating of a cloud due to quasi-virial collapse. That is, it collapses sufficiently slowly such that at every stage of the collapse, I can assume that the virial theorem is valid. And in such a situation, if suppose I have time t1, when it is virialized, I have this equation. Since it remains virialized under contraction, this is the equation at the later time t2. And if I subtract these two, I get twice the change in kinetic energy, twice the change in total kinetic energy is equal to negative of the change in potential energy. Now, since potential energy is negative, collapse actually makes the potential energy more negative, and hence the change in the total potential energy under collapse is less than 0. So delta PE is less than 0. And so this minus delta P is basically mod of delta P. So the total kinetic energy, total change in kinetic energy is equal to half the change in potential energy. And since the potential energy decreases, so half the potential energy goes to increase the kinetic energy, and this leads to increase in temperature, because the random kinetic energy is basically a measure of the temperature of the gas particles of the collapsing cloud. Is this chain of logic clear?
Yes.
Yes.
Okay. Okay. So if those people who are not answering, I will assume that it is clear to them. Okay, it's your responsibility to ask me. Okay, and it is believed that when you start with a cloud of gas and dust, and it starts collapsing under gravity, this is how the temperature of the gas increases. And at sufficiently high temperature, fusion kicks in. And then once the fusion is sufficiently large, then just a minute. Once the fusion is sufficiently large, it halts the collapse and the system becomes a star and is in stable equilibrium and stops collapsing. Now, there is another very interesting concept, very interesting consequence of collapse of this one. And it was a, it was a wrong, okay, so let me just put it, what is the consequence of that? Now, here I see that only half the potential energy goes into increasing the temperature. The question now arises, what happens to the rest of the half? It was believed that the rest of the half of the potential energy actually is radiated out. And before the discovery of fusion, it was believed that this is the mechanism because of which sun is emitting radiation. Because they did not know, beginning of 1900s, they did not know what was a fusion. They didn't have a concept of fusion. But one knows that sun is radiating. And the only way they could get the sun to be radiating was this. Now, it was a very nice theory, but it was wrong. And it was wrong because of the following reason. Now, if we calculate the total, okay. So now, if the mass of the sun is m, then the total potential energy is roughly gm square by r. And so, the total kinetic energy, thermal energy of this system will be gm square by 2r, which from Virial theorem we know. Now, if this much thermal energy is to be radiated, we know what is the luminosity of the sun. Luminosity of the sun is equal to L is equal to dE by dt. That is the energy emitted per unit time. And so, this total thermal energy divided by luminosity will roughly tell me the lifetime of the sun. That is, for how long will this total amount of potential energy which is stored in it for radiating can keep the sun alive. And if you put in the numbers, we get for sun, it is about 3 into 10 to the power 6 years. Now, this is a large enough time, and people were happy with this. Now is where an example of astrophysics drawing from various different sources of knowledge comes. There is no problem with this, but then what is the spelling correct? I don't know. Paleontologists found that there were fossils of prehistoric living beings about billion years ago. Now, clearly, life not possible without sun. So it means that the sun should have existed even a billion years ago, which means that the lifetime of the sun being 3 million years ago does not fit into this, and this mechanism was ruled out. This, of course, brings us to another question, which is fine. We now know that this is not the mechanism, but what was the mechanism? Nobody knew at that time. So, mechanism of energy generation in sun, a problem in early 20th century. And it required the discovery of nuclear fusion to solve this, to find out that the energy generation of the sun has to be something else. Is this clear?
Yes, sir.
Any questions? Any questions about this?
So what happened to the remaining potential energy?
Which remaining potential energy?
Like the one half is for increasing the temperature.
Huh?
The other half, which is now not.
The other half is indeed radiated out if it is contracting. So the only way they could say was the sun is contracting very slowly so that we don't see it, and this radiation is coming out. Now we know that from nuclear fusion, sun is not contracting. Even without contracting, it is still radiating because of nuclear fusion.
Okay, sir.
Okay. But on the other hand, when a cloud is collapsing to form the star, together with increasing the temperature, one of the collateral effects which happens is radiating this energy out. I mean, of course, it is not of the kind which you can form stars, but there is indeed a radiation being radiation is being given out because of this quasi-virial collapse. Okay? Is it clear?
Yes.
Srinta?
Yes, sir.
Is it clear? Oh, sorry, Sujana. Is it clear?
Yeah.
Yeah.
Yes, it's clear.
Okay. Fine. Okay, so now we will go to another topic, which is gravity is independent of distance. Oh, sorry, is independent of direction. That is, the gravitational potential energy is only equal to the modulus of R. Hence, no direction dependent. Further, if no anisotropy due to environment, then spherical symmetry is expected. Is this clear, this chain of logic?
Yes, sir.
Hello? Is this clear?
Yes, sir. Yeah, Shesh.
Yeah. Okay. Good. Fine. So this is one thing. So spherical symmetry is one. The other thing is stars are stable structures. That is, shape and size do not change over long time scales, which is of the order of 3 into 10 to the power, which is of the order of something like between 10 to the power 8 to 10 to the power 10 years, depending on what is the mass of the star. Which means I can assume, this means assumption of hydrostatic equilibrium. Okay. Now, what does hydrostatic equilibrium mean? It means no time dependence. So with these two considerations, with one, spherical symmetry, and two, hydrostatic equilibrium, we need to construct simple theory of stellar structure. Okay. So now let us look at the following. There is a certain derivation given in moon, but it is not completely correct, and basically, like, two mistakes sort of compensated. So I will do a more rigorous calculation for this. Okay. Now, aside on fluid mechanics, some very basic thing about fluid mechanics I will take, which is useful for us. Now, there are, of course, when you want to do fluid mechanics, there are various issues like what is a fluid and so on. We will not go into those intricacies, except to say that in fluid mechanics, fundamental entity is a packet of fluid which is large so that number of molecules are large and small enough so that physical parameters do not change significantly within the packet. Okay. Okay. So now let us take a certain packet of fluid of volume delta V density rho, pressure P. And let U be the velocity field, by which I mean the following, that rho P U all functions of position and time. Is the setting up of the problem clear?
No.
Okay. So now what I mean is, okay, so suppose you take water. Actually, water is made of small molecules. But when you do fluid mechanics of water, you don't consider the granularity of the molecules, right? You assume that it is kind of a continuous medium. Do you get it? Hello?
Okay.
Okay. So what do you mean by a continuous medium? It means, suppose I were to consider this packet to be so small, there are only 10 particles in it. I can't consider it to be a continuous medium. So it should have sufficiently large number of particles so that I can talk about the average density within the packet. And the packet should not be so large that here the density is different and here it is different. If this is so, I cannot assign a density for this whole packet. So basically, there are two limits. One is it should be large enough to accommodate sufficiently large number of molecules to have a continuum approximation, and at the same time, it should be small enough that the pressure and density and other parameters do not vary significantly across this, and you can assign one density to the center of mass of the packet, which can be taken as a density of any place inside the packet. Is this clear?
Yes.
Yes, sir. Yes.
Is it okay?
Yes.
Okay. So now, this is having this. Which is the velocity of the packet will be equal to minus, okay, so wait a minute. So what I will do is mass into density. Okay, I will do one thing. I will actually backtrack on that. I'll just give you the, I'm not sure whether I should, okay, so let's see. So I have du by dt, which is equal to the, okay, wait. So mass delta m du by dt will be equal to the total force on the packet. Now, the total force on the packet is because of two reasons. One is difference in pressure. And two, gravity. Okay. And I will just give you this result of fluid mechanics, that this can be written as rho du by dt is equal to minus the gradient of the pressure plus the gravitational force. Is this okay? I mean, this I'm just giving you as a result. This can be looked at in the following way. See, pressure is force per unit area. And so gradient of pressure is something like force density. Okay? Which divided by density is like acceleration, which is what this is. Okay? Here I have to, just a minute. So it is, I will call it acceleration due to gravity, which need not be constant. It can be gm by r square. This into density. This is what it should be. So this is the force per unit volume due to gravity on a unit volume. This is the pressure. This is the force density, and this is the resultant of it. And so we have du by dt, which is the acceleration of this packet, will be equal to minus 1 by rho gradient of the pressure, okay, minus when suppose you have a spherical symmetry, okay. So we can actually simplify it here itself. First of all, I will have hydrostatic equilibrium. Which means no mass movement. Right? If it is in equilibrium, it will be static. There will be molecular motion, but there will not be any bulk motion of matter. And hence, U will be equal to 0. Okay, U will be equal to 0. And then because of spherical symmetry, we have minus gradient P plus the gravitational acceleration into density will be equal to minus dP by dr minus gm by r times rho, both of them with a cap r. Is this okay?
Okay.
I have just written the gradient in spherical symmetry, and the acceleration due to gravity because of a spherical distribution of mass. Is this fine?
Sesh, can you summarize this once again?
Okay. Yeah. So let me tell you what is it that I have shown and what is it that I have asked you to take for granted. First of all, I have motivated how there will be the acceleration for a packet of fluid. Then written it in terms of pressure and density. I have not derived it, but I'm just giving you the result. Okay. And now, so this is my equation where U is the bulk velocity field of the fluid. And when you have a hydrostatic equilibrium, we don't have any mass movement. And so the bulk velocity is 0. Is this clear? I mean, if suppose you have a glass of water and water is static, it means there is no bulk motion, right? Is it okay?
Yes, sir.
Yes.
Okay. So U is 0. Now, because of spherical symmetry, I write my gradient in the spherically symmetric form in this way. It is minus dP by dr times the unit vector r. And the gravity G will be, gravitational action will be minus gm by r square times unit vector r multiplied by this density. And so I have 0 is equal to, from here, minus dp by dr minus gm by r square rho. Now, what is this m? What is this m? Anybody? Hello, can you hear me?
Yes, sir.
Yes, sir. Is it the mass of the bulk?
Yeah, but there is catch there.
Hmm.
See, let me just come back. So suppose I have a spherical configuration of gas. And I'm talking about, say, a point inside which is at a distance small r. And suppose this total size of this is capital R. I am talking about the packet which is located here.
So everything inside that radius will be.
Exactly. So it means that gravity will be provided only by the mass within this. Okay. Okay. Now, which means that the correct way to write this is dp by dr is equal to minus g m of r, that is mass contained within this radius r divided by r square into rho. Is this clear?
Yeah,
So
Shesh.
here P is the pressure at the radius r, rho is the density at the radial distance r, whereas m of r is the total mass contained within that radius r. So this is a non-local object. And what is m of r? Because of spherical symmetry, m of r will be equal to 4 pi integral rho of r prime square dr prime 0 to r. Is this okay? Okay?
Yes.
Fine. Now you can just write this, and actually, although it looks like a very simple equation, this is not even a differential equation. It is an integral differential equation. I'll just write it again properly. Just okay. So you understand? So this is actually, it is dp by dr is equal to minus g rho of r by r square into 4 pi multiplied by integral 0 to r rho r prime square dr prime. Is this okay?
Yes, sir.
I mean, basically this quantity, sorry, let me write it this way here. This one. Are you with me?
Yeah, yes.
Yeah. What about others?
Yes, sir.
Yes, sir.
Yes.
Hey, don't be very
Yes, sir.
hesitant saying it here. If it's not okay, tell me. I mean, okay, please ask me if there is anything. Otherwise, there's no way I will know that it's not clear. Okay. So this is called the equation of hydrostatic equilibrium in stars. Okay. Now, what we need is to solve this. We also need P as a function of rho, right? How does pressure, say for example, if it is ideal gas, then you know how P goes as rho, but there's a temperature involved. Okay. So this can be written as in some way, dP by dR is equal to dP by d rho into d rho by dr. And that is equal to this thing, 4 pi g rho r by r square integral 0 to r rho r prime square dr prime. Is it clear? So, so it is an equation in rho, but we need to know what is the relationship between pressure and density. And we will have opportunity to delve into very great detail about different kinds of pressures and densities and hence get the stellar structure. Okay. So, but one can still do a few things here with this. For example, suppose I know I can ask the following question. Okay, so there is one more thing. So this is a differential equation, but what I also need is boundary conditions. Okay. Now, for boundary conditions, what is boundary condition on the surface of the star? Any
Density
guess?
vanishes.
Pardon?
The density vanishes. There's no.
No, not exactly. It need not vanish. Okay. I'll tell you what happens. What is it? It was Ariel, right?
Yes, sir. I mean, you
So
said it's not
what
the
else
case.
can vanish? It's a pressure.
Pressure.
And the reason for this is the following. I have a star here. Now, at any point, because of hydrostatic equilibrium, at any point, the pressure here is equal to pressure here. P out equal to P in, right? Because if it is not so, then one of the pressures will be larger and the system will start collapsing. Is it clear?
Yes, sir.
Okay. Now, if you go to the boundary of the star, what is the pressure from outside?
Zero.
Zero. Hence, for having hydrostatic equilibrium, the pressure from inside should also be zero. Hence, the boundary condition is P on the surface is zero. This is the boundary condition. Now, it can so happen that the equation of state is such that Ps equal to zero could imply rho on surface is 0. Not necessarily, but it is possible. So, fundamental boundary condition is P on the surface is 0. All right?
Yes, sir.
Okay. Fine. So now let us consider some typical examples, some examples. Let us consider the variation of, suppose I have a star, some examples of P rho r. Suppose I have a rho of r is equal to 1 minus r square by capital R square times the central density. Suppose I have such a density. All right?
Yeah.
Okay. Fine. Now let us see what will be the pressure variation. So now if suppose I have this, then what is M of R? M of R is equal to 4 pi integral 0 to R rho of R prime square dr prime, which is equal to 4 pi integral 0 to R rho C 1 minus R square by R prime square by R square R prime square dr prime, which is equal to 4 pi rho C R cube by 3. Is that okay? Minus R cube by 3 minus 1 by R square R to the power 5 by 5. Is it okay? I've just integrated it. Are you with me?
Yes, sir.
Say, I have
And
one
this
doubt.
is equal to mass. And so I have mass into radius, mass at a radius r multiplied till a radius r multiplied by rho as a function of r is 4 pi rho c square 1 minus r square by r square times r cube by 3 minus 1 by r square r5 by 5. And so I will have, this is my M of R. And then if I divide it by R square, I divide it by R square, multiply by G, minus, this is equal to dP by dr. All right?
Yes.
So it means, so I can write this as dP by dr is equal to 4 pi G rho C square into 1 by R square, you know, minus, this is R cube, right? No, it's R square. 1 by R square minus 1 by capital R square into R cube by 3 minus 1 by R square R5 by 5, which is equal to 4 pi G rho C square R by 3 minus R cube by 3 R square minus r cube by 5 r square plus r5 by 5 r4. Okay?
Yes, sir.
Is it fine?
Yeah, yeah.
So I have P is equal to the integral of this. I have 4 pi g rho c square into r square by 6 minus r4 by 12 r square minus, oh, this can be combined. Okay, sorry.
I guess you missed the minus sign there.
Pardon?
I guess you have missed the minus sign in front of G.
Ah, okay. Thanks. Yeah. Yeah. P is equal to, okay, minus G plus no. Sorry, what am I doing? Sorry. Okay, and so P is equal to minus 4 pi g rho c square r square by 6 minus 24, no, square by 6. This will be a 3. What am I talking? 4. So it will be integral R4. So R4 by 30 R square plus R6 by 20 by, I think, 30 R4. I mean, check. Okay. Plus, pardon?
The second term would be 2r by 15. 2r per 4 by 15.
Which one? Where in this step?
Once again. I think it's 2r per 4 by 15 r square. Yeah, the second term in the integration.
Yeah, it's
Here.
2 by 15.
Yes, sir, it's 2 by 15 r to the power 4.
2 by 15 hours.
R per 4
Oh, yeah,
by
yeah,
4.
yeah, yeah. Sorry, sorry. Yeah, yeah, of course. Okay. And this will be okay, right? This one.
Yeah.
This is okay, no?
Yeah, yeah.
Okay. So this is the thing, but this is a constant of integration. How do we determine the constant of integration? That's where the boundary condition comes. I ask, what is the pressure on the surface? The pressure on the surface is 0, which is equal to minus 4 pi g rho c square r square by 6 minus 2r square by 15 plus r square by 30. Is it okay?
Yes, sir.
Plus constant. And this will be equal to minus 4 pi g rho c square. And this will be what? 30. This will be 5 minus 2 plus 1, which will be 6, which will be 5. So I think this will be r square by
5 minus 4 plus 1.
y minus 4. See, this is 30.
Yeah, 6 5 is 30, 15 2 is
5.
30.
And then this will be 2. And this will just be 1. So it will be 4. 4 r square by 30. So 2 r square by 15. Is it correct? Today I'm sort of making a lot of silly mistakes. So this will be what? This will be 6 into 5, so 5 r square. This will be 2. This will be 1, 5 minus 1 by 2. So this will be minus 1, 4, 4 by 30, 2 by 15, plus c, which will be equal to 0. What this means is the constant of integration is 4 pi g rho c square. I mean, this by 50. So you have got this thing. So you know what is the pressure at any point. Is it okay?
Okay.
So the pressure at any point R is given by 8 pi g by 15 rho c square into this thing. R square by 6 minus 2r4 by 15 r square plus r6 by 30 r4 plus 8 pi g by 15 rho c square. Okay. So now you can ask the question, what is the pressure at the center? The pressure at the center will be, central pressure will be when r equal to 0. So the central pressure will be equal to 8 pi g by 15 rho c square. There is a mistake somewhere here.
Sir, I
So
think
that
Yes.
will be 4 by g.
yeah.
Is r square missing?
The value will be 1 by 50.
This is what is missing, right? No. What's the problem?
The second term,
This one.
sir, that small calculation on the, it's actually 5 minus 4 plus 1. So there's a factor of
This is 4
15.
plus 1.
Yeah,
8 minus
it's
4 plus. Oh.
2 by 15. Huh.
Aha. Okay. Yeah. So it is 2. So it will be 4. Yeah. Okay. So it will be 4 or whatever. I mean, you can just correct it. Okay. So you understand how I am getting the central pressure.
Yeah.
All right. So this is an example of how central pressure can be calculated. Okay. And yeah, so this is one thing. Now, okay, so I will just do one more thing here. Today we'll just finish that. It is, so I have dP by dr is equal to minus g m rho by r square. And so if I calculate the central pressure, this will be P, sorry. So this will be dP by dr integral 0 to capital R will be equal to minus G m of R rho of R by, this will be R square integral 0 to capital R dr. Now, first of all, from this, let me remind you of the dimensional analysis which I was doing earlier. From dimensional analysis, this left-hand side will be of the order of pressure difference divided by the radius of the star. Since surface pressure is 0, this is central pressure by radius. And the right-hand side will be Gm by R square and M by R cube for density. And this will be Gm4 by R5. And these two imply that the central pressure is equal to Gm square. gm square by r to the power 4. So we will do one thing. We will just stop here. We will be taking up some very specific ways in which you can put bounds on the central pressure without knowing the exact density profile of the star. And we will find that they all will be of the order of this. Is this okay?
Yes, sir.
Okay. I think today we'll stop because I have some work today. So next Saturday, we will not be meeting, but the Saturday next to that, we will continue. In the meantime, you have any doubts, you can always write to me.
Okay, sir.
Okay?
Okay, sir.
Okay. Okay. Thanks a lot. I
Bye.
will make the notes, problem set, and then upload it.
Okay.
Bye, sir.
Bye. Bye.
Thank you.